Today we're going to do the first lesson of Ingonyama's Accelerating Cryptography course. The course today will deal with modular arithmetic. This is a list of references that have been used in creating the course, and you can check them out later. The agenda for today's lesson is as follows. We will start with reviewing why modular arithmetic is important. We will then continue to discuss multiplication, primarily Barrett and Montgomery. We will show some tricks that allow us to exchange between Montgomery and Barrett within applications. We will discuss RNS, which is residue number systems, and then some special primes. And let's get started. Okay, the first section of lesson 1 is going to be an introduction. We'll start with a few applications. We're not going to really go through them, but just examine what type of arithmetic they use, just to understand why we need modular arithmetic here. So the first example is a one-time pad. One-time pad is a symmetric scheme. It assumes that we've got a shared secret key, and it builds on just additive homomorphism within a finite group Cn. Our next example is RSA. RSA is an asymmetric scheme. And RSA actually builds on this finite ring that whose size is actually a multiple of 2 primes. It's a different structure, but again, it uses arithmetic within this finite ring to achieve the secrecy. Finally, there is Attai's one-way function. And Attai's one-wave function actually examines a lattice over a finite field or a lattice over a finite ring, and it actually uses the nature of this finite lattice to create some sort of one-way function. So, in summary, why do we actually need modular arithmetic? Well, there are various reasons, but 3 of them, maybe the 3 main ones, are: 1, it gives us a finite range for computation, which is good for machines because machines work over a finite range. It gives us algebraic structure, which we often need for reversibility. And fundamentally, it allows us to, the modular structure allows us to create one-way functions in a way that continuous type of arithmetic will actually be sometimes impossible to use. Some basic algebraic structures, again, I'm not going to go through them because that's not the actual point of the lesson, but we go all the way from sets to groups, which are sets with a single operation, to rings, which are sets with 2 operations, and finally to fields. There are a few examples of these algebraic constructions here. Typically, a field will be of size of prime size, or extension fields, which would be of size that would be some power of a prime. Though there is an isomorphism between polynomial rings over fields to extension fields, and so on. What we are mostly interested in this lesson is actually exploring the low-level computations, and we take the basic operators of addition and multiplication. So addition, if we add inside some, let's say, finite group, right? Then if we look at the example that I've got here, this finite group actually is limited at 7. It actually doesn't get to 7. So really, it actually goes from 0 to 6, right? And then it's modulo 7. And then we can see that if we take two numbers within this ring and then we add them, that we actually go out of bounds, right? Because if the bound is here, right, we go out of bounds. And what happens is that we actually represent within this group, we represent things by their residue. So when we add two things, it tends to be quite simple because after addition, we will only have, we will be technically in the second region, right? If we call this maybe region number 0, this will be region number 1, then we can either be after addition in region number 0 or region number 1. In our case, we're in region number 1, so we actually need to care about what is the value here in region number 1, right? And we assume that the regions are basically just copies of one another, and we need to know, okay, how much have we overflown into region number 1? And the way to do it is by decreasing 7 from the result. Now, that's quite simple, but when we go to multiplication, as you can see in this example of 5 times 4, we actually start accumulating many of these regions, and we actually land in a region that is very far away. And as the fields or groups or rings more correctly grow, that there can be many copies of the basic size that we need to remove, and it's often hard to directly compute this. And this is basically what modular multiplication is about, and we will discuss how to do this efficiently in this course.